Let's talk about the calculations for experiment 7b. So as we go through the experiment, setting up the calorimeter, we're going to be recording a lot of information. The mass of the calorimeter when it's empty, adding water and weighing the calorimeter with the water in it, heating water, we're going to have some temperatures, and then a final mass. And as we go through the other sections, we'll see that we're collecting similar information. We're going to be collecting initial temperatures, final temperatures, and masses. And so these are going to end up in our report over here. So in the data section, the mass of the empty calorimeter, the calorimeter with the cold water, temperatures, etc. Data for the complete reaction, for the step 1 reaction, and for the step 2 reaction. So then we get to the calculations, which are confusing because there are so many of them, and all the letters and things are similar, but the actual calculations themselves are very straightforward. So in the calculations section, it says show one example of each calculation, including units. So I've labeled the calculations that you need to show. Showing the calculation means that you write all of the numbers that were multiplied or subtracted, and you have an equal sign, and you write the final answer. I encourage you to work your calculations out in your notebook first, because a lot of times your first try is kind of messy. And once you know what you're writing, then copy them neatly here. I want you to use the data from trial 1. You're doing the same calculations for trial 2. Don't write them on the paper. You can write them in your notebook if you want to, but you don't have to. These calculations will show me what you were doing for the other parts. Now this is important. Underline the last significant figure and keep 2 extra digits. This is a long series of calculations, and if we round at each step, we can end up with some serious error at the end. So we're going to follow best practices with significant figures. And with each calculation that you do, identify the last significant figure, underline it, and then keep 2 digits after that to use in future calculations. Okay, so first up is the mass of the cold water. So you're going to look back through your data, and what you need for that one is the mass of the calorimeter and the cold water, and subtracting the mass of the calorimeter. Now, the way that the words are written out here can help us if we get a little confused as to what we should be adding or subtracting or whatever. So we have the, writing and talking at the same time. I should be able to do this. We have the calorimeter plus cold water. And we have the mass of the calorimeter. Okay, that's the mass of the calorimeter plus the cold water. If I look at the words and subtract, calorimeter minus calorimeter is nothing, and I end up with cold water. So by taking the mass of the calorimeter and the cold water, subtracting the mass of the empty calorimeter, I can find the mass of the cold water. So down here, I want you to write those numbers. Write the mass of the calorimeter and the cold water with its unit, minus, and the number for the empty calorimeter equals, and then write mass, and follow the rules for significant figures. So where do we put that answer? Well, that answer goes in a results table. So here, the mass of the cold water for trial 1 will go right in here. The next calculation listed is delta T for the cold water. Remember that delta is always final minus initial. So delta T for the cold water is the final temperature minus the initial temperature. So we're going to go back to our data table. And what we have here, we have an initial temperature for the cold water, so we're going to need that. We also need a final temperature. The final temperature listed here says of the mixed water. This is the final temperature of both the hot water and the cold water because they were mixed together and they came to the same temperature. So we're going to use this final temperature, subtract the initial temperature of the cold water. That'll give us this value, which we will write down here, delta T for the cold water. In parentheses it says also delta T cal. We're going to need the change in temperature for the calorimeter in a later calculation. The calorimeter was sitting there with the cold water in it. We added the hot water, everything warmed up, and the calorimeter ends up at the same temperature as the mixed water. So the calorimeter experiences the same temperature change as the cold water. This is just a note for later. Next in the list is Q cold. Now, Q equals MC delta T. So Q cold not sure what happened there. Q cold equals the mass of the cold water times the specific heat of the cold water times the change in temperature of the cold water. So this and this, the mass and the temperature, were just calculated. Here's the mass, here's the temperature. C is not a mystery. C is the specific heat of water, which is 4.184 joules per gram degree Celsius. So you calculate Q cold. You write Q cold in the box for Q cold, right? Step by step. Next, mass of warm water. Well, you're going to calculate this very similarly to how we calculated the mass of the cold water. Here we have the final mass of the total mixture. So what's in that? I didn't write it all out because there's not enough room in the box there. That's the calorimeter plus the cold water plus the warm water. I want the mass of just the warm water. So what I want to do is I want to subtract the mass of the calorimeter and the cold water. Calorimeter plus cold water. And when I subtract those, this minus this is 0, this minus this is 0, and I end up with the mass of the warm water. So that's how I'm going to find the mass of the warm water. Delta T for the warm water, again, final minus initial. The final is the same temperature as for the cold water, but the initial temperature is different. Q for the warm water, again, Q equals MC delta T. Q warm equals the mass of the warm water times C for the warm water times delta T for the warm water. So we just calculated the mass of the warm water right here and delta T for the warm water right here. What's C? Well, C is still 4.184 joules per gram degree Celsius. All right, so we're going to record that down here. Q warm, right here. Okay, now we need to calculate Q cal. So this is where we go over to our discussion in the pre-lab lecture. Here we go, heat capacity of the calorimeter. Yeah, it doesn't work over here, okay. Qcal plus Q cold plus Q hot equals 0. We just calculated Q hot and Q cold, warm, hot, same thing. So to calculate Qcal, we're going to add those two values together and change the sign. So Qcal here is equal but opposite in sign to Q for the cold water plus Q for the warm water. So plug those values in, record Qcal. Ccal, again, comes back to what we talked about over here. This is the equation we're using. C, the heat capacity for the calorimeter, is Qcal divided by the change in temperature. So Ccal equals Qcal divided by the change in temperature. Qcal is what we just calculated here, Qcal. Delta T, this is the change in temperature for the calorimeter. Sorry, here we go. Also T, delta Tcal. So it's that same temperature that we calculated for the cold water. So there we get Ccal, and we're going to put that in here. And then trial 2, you don't need to show these calculations, but you're going to do them in the same way. Same calculations, slightly different numbers. You'll go through. It's best to just do them in order, fill them all out, and you'll get a Ccal here. These two Ccals are going to be a little different because the measurements here are not super precise. So we're going to use the average Ccal. So take this value plus this value, divide by 2, just simple average. And again, underline the last significant figure and keep 2 extra digits. So then we're going to go into the complete reaction. And there's a place up here to show many of these calculations. And it says calculations for step 1 and step 2 reactions will be similar. So I'm not going to make you write all of it out because I think that's busy work. But here, the mass of the solution. Again, that's the calorimeter with the solution minus the empty calorimeter. The change in temperature for the solution, final temperature minus initial temperature of the solution. Q for the solution, well, Q for the solution equals the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. Sold. Here's that C again. Do we use a specific heat capacity of water? Well, was it just water in the solution? No, it wasn't. So if we go through the procedure all the way down to the bottom where it talks about the calculations, you may assume, oh, it won't let me even write over there. Okay, whatever. You may assume the following specific heat capacities in your calculations. So for the copper 2 sulfate solution, 3.82 joules per gram degree Celsius. Copper sulfate and ammonia solution, 4.05 joules per gram degree Celsius. So you're going to use these in a couple of different places. So in this complete reaction here, the complete reaction, we took the ammonia and some water and put them in the calorimeter, and then we added copper sulfate. So in this complete reaction, we have copper sulfate and ammonia. So we want to use the heat capacity for copper sulfate and ammonia, which is the 4.05 joules per gram degree Celsius. Then Qcal. Well, Qcal equals C for the calorimeter times the change in temperature for the calorimeter. This C here is the average we calculated. We're going to use the average C from the first part. Well, let's be more specific. From table 5. So that's this one right here. So that's the average C. We need the change in temperature for the calorimeter. And here we're recording for the complete reaction, we're recording in table 6, the mass, the change in temperature for the solution, which is also the change in temperature for the calorimeter. So we've got Qcal is C, the average C, times the change in temperature. It's the same as this temperature change. Q reaction. So this is the thing that we're actually wanting to measure, but we can't measure it directly. So all of the energy that went into the solution and to the calorimeter had to come from somewhere. It came from the reaction. And just referring back to the introduction here, Q reaction plus Q solution plus Qcal equals 0. So Q reaction, we're going to take Q solution and Qcal, add them together, and change the sign. So here Q reaction is equal to Q solution plus Qcal, and then change the sign. Okay, so that's going to give us an amount in grams. I'm sorry, in joules, an amount in joules. So you're going to record that right here, Q for the reaction. I have to fix the report sheet because next up is the moles of copper sulfate. So moles of copper sulfate, so these need to be switched. Try to fix that on your report sheet. Moles of copper sulfate, you've got grams of copper sulfate. And just calculate the moles using the molar mass. What was the mass? Well, that was measured right here, mass of copper sulfate. So take that mass, apply the molar mass for copper sulfate to get the moles. So Q is the amount of heat given off by this specific reaction in its current size. Delta H refers to the enthalpy of reaction for this chemical equation. And convention says that delta H should be written for an amount specified in this equation in moles. So for 1 mole of copper sulfate, we want to know what delta H would be. So we calculated delta H for a certain number of moles that we calculated right here. So I'll scoot over here. Delta H for the reaction is going to equal Q for the reaction divided by moles of copper sulfate. And so that will give us joules per mole. It's specified here kilojoules. Okay, so we need to convert this This will be in joules. And so we're going to have to apply a conversion factor to convert to kilojoules per mole. So table 6. We're down to here. Then there's a second trial. You're going to do those calculations in the same way. Ideally, these would be the same. They're not going to be exactly the same. So we're going to use the average. So we'll record the average right there. I explained how to do the calculations for the complete reaction. The calculations for step 1 reaction and step 2 reaction are going to be very similar. Again, finding the mass of the solution, the change in temperature, Q for the solution. Using that change in temperature combined with the average C to find Q cal, and from those two finding Q reaction. Moles of copper sulfate, converting this into a delta H, doing it for the 2 trials, averaging together. And then again for step 2. The one thing you need to watch out for is which heat capacity do you use. So let's look at what we've got here. So the complete reaction. In the complete reaction, we had copper sulfate and ammonia, and so we used the 4.05 joules per gram degree Celsius. In step 1, we're dissolving the copper sulfate in water, so there's no ammonia present. So looking down here at the end, the copper sulfate with ammonia, we use that in the complete reaction. But this copper sulfate solution alone, this value we want to use for step 1. And then step 2, we'll also use this because we're taking the copper sulfate from part 1 and mixing it with ammonia. So use the 4.05 for the complete reaction, and for the step 2 reaction, use the 3.82 for the step 1 reaction. And you'll get the average again, and so then here are the results for Hess's law. Record the average you got for the complete reaction, the average for step 1, the average for step 2. The percent error, the calculation goes back up here in the calculations section, and how to do that calculation is talked about over here, right here. So we're going to use the sum of delta H for step 1 and step 2 as our experimental value, so that goes in here. And we're going to use the complete reaction value for our theoretical, so that goes here and here. And you can calculate the percent error. So there's lots of results tables. And then there's a little discussion section here. I want at least one complete sentence discussing your results. Things you should think about and most likely include. What does Hess's law predict about the enthalpy changes for these reactions? So say something here in your discussion that lets me know you understand what's going on. Looking at your percent error, do the results support Hess's law? If they don't, if there's a problem, give one possible source of error. And human error or calculation error, that's not acceptable. It needs to be something else. And then in the conclusion, not asking for a whole lot, but state the reaction that was studied. So give the reaction. You could write the reaction out or you can describe it in words, but you have to say what reaction we're studying. Give the average heats of reaction for all 3. the step 1, step 2, and the complete reaction, and then explain how the percent error was calculated and what the percent error was. And as always, if you have questions, please ask me.